which will also lead to the same result, is I can do this. I can act on H acting on psi gives you chi. This H can act on this, right? It acts on psi star. Okay? This is the statement that you can act this to give you chi, and this will give you a new function which is chi star, which is same as root 2 root n. So what you have here by this action is chi star chi dx from 0 to 1. And what you have now, 2 root n into 2 root n is 4 times n, integrated from 0 to 1, it will give you some number. Actually 0 to 1, because it is a constant, 0 to 1 gives you 4 root n, that is all. Okay? So that is the answer for H square, it is not 0. Actually H square average cannot be 0 for a non-pure eigenstate. It cannot be 0 for a non-pure eigenstate. It has to be a number. So this is the easiest way I can compute. Well, if you don't like this, the better, another way of doing this is that psi which I have, which is root n x into x minus 1, it is some function. Let me try to plot it. It is some function like this. It is a parabola. Actually, it is a parabola. As you know, y is equal to x square minus some function, right? That is what is that parabola. So try to you just assume this is a periodic function like this, because all our eigenfunctions are sine functions, right? Sine n pax by l. So you can expand this. You can expand this an sine n pi x by n pi x, because I have made the, you can expand it. Fourier series. I am doing Fourier series. Have you seen Fourier series? So this is the expansion you have to do. If you want, you have to find the coefficients an, right? The coefficients an are found by this coefficient an is actually 1 by some 2 pi 0 to 1, actually 0 to pi, 0 to 2 pi, and then x into x minus 1 into sine n pi x. This is that integral. You have to integrate this, that function f of x multiplied by sine n pi x, integral from 0 to 2 pi will give me that coefficient ans. You find all the coefficients. All the coefficients will be non-zero. How many coefficients will be there? All infinite number of coefficients. But they all will decrease. As n increases, the value will decrease. The value will decrease, and that series is what people will call as a convergent series. Okay? Now use that series, etc., and compute your H square average. You have to compute in that series. Now that is like when you do the H square average for that series, so you will get an infinite series. Actually, you will get an infinite series, and the value will be some finite number. Since I have cooked up by other way, the value of that sum is equal to some 4 times n, okay? That is what you will get. Even though that series is very large, okay, it will be only 4 times n. It is like you can have an infinite series. You can have an infinite series whose sum is simply a finite number, and in some cases you can easily find this finite number. I will tell you one simple example. If I have an infinite series like 1 plus half x plus half 1 by 2 factorial half sorry x square, that is all. Okay, x square plus x cube. Let me consider this series. I want to find the value of this series when x is equal to half. When x is equal to half, what is it I will do? I will take 1 plus half square plus half cube, etc., etc., up to infinite number of terms. Now, what is the value of that? What is the value of that series which I am writing? This series is 1 plus half square plus half cube, etc., etc. There are two ways of finding it out. What are the two ways? Again, it is a geometric series. It is a geometric series, you know how to find it. But anyhow, I know the answer, because if I have this expansion 1 divided by 1 minus x, 1 divided by 1 minus x, if I expand it, that is what I will get. That series is what I will get. Okay? Now, if you sum all of them, you will get a number. I do not know what is that number is. Probably you may find it out. But when I put in this series, in this 1 by 1 minus x is equal to half, it will be 1 by half, which is 2. So, the answer is 2. Okay? You do not have to sum all the series, all the terms in some cases. Okay? So, that is the idea. So, even in this case of whatever I have done here, an, find the coefficients and then sum the series, h square average, you will find it. Okay? And the answer is only simple, what I have already given. So, it is very simple to work out. Now, it is more complicated. It is more complicated for several reasons about what I call as what I said. In fact, my friend was objecting to that. I said that there is a Hilbert space, you do not have to worry about it, it is only ordinary vector space, etc. This is the way I gave the lecture. He actually confronted me, how can you tell that? Because it is actually a more complicated mathematical structure. Do not bother about the issue, but the thing is, you can have 2-dimensional vector space, 3-dimensional vector space, or you have two components. A 2-dimensional vector space will have a column vector a1, a2. If it is a 3-dimensional vector space, a column vector a1, a2, a3. This is the way it will go on. There is no problem with many of these things. There are such matrices, you can multiply, etc., etc. As I told you, the problem becomes whenever that matrix becomes infinite in size. It is an infinite by infinite matrix, okay? And that becomes more complicated. There are several things which you have for finite matrices. However large that finite matrix is, it can have million by million matrix, trillion by trillion matrix. It obeys a simple result like trace of AB commutator is always 0. It does not matter how big the matrix is. But the moment the matrix is infinite by infinite matrix, that is no longer true. So, there are several new things that happen because of this fact that there are infinite dimensional matrices which you have to deal with. Why is it you have to deal with infinite dimensional matrices? You can ask the question, said my wave functions are square integrable functions. I want to expand it in some basis, right? Any vector is expandable in some basis, right? You will write a1i, a2j, a3k, etc. You can write it. So, if you have infinite dimensional space, you will write infinite basis will be infinite. That is what? In our case, sin n pi x by L, sin n pi x. Each function is sin n pi x. So, n is going from 1 to infinity. So, how many, the vector is infinite dimensional. If I want to write it as a column, I will write the first one is 1 0 0 0, second one is 0 1 0 0, and third one is 0, 0, 1, and up to infinite number of terms I will write. That is what that vector space is. Okay? Now, whenever you have such kind of vector spaces, like this example which you have here, there is some really funny things happen, and it makes life little more complicated. And that is the origin of this kind of problem. Yes, please.
While calculating an, the limits are going from 0 to 2 pi or?
Well, actually 0 to 1 because I have kept the length of the thing.
Okay.
So, usually people expand it in a basis with 0 to 2 pi because that is what the regular functions are. So, that is the thing, it is 0 to 1 in this case. Or if you have 0 to a, it is 2 pi x by a. That is what will happen.
Sir.
Okay, anything else?
Sir, so when you said like psi star h square psi can be written as like the, since it is h is Hermitian, it can act upon psi star. I don't think it's right because I don't think it's correct.
Go ahead, I'm listening.
I don't think it is correct. Like if I do like integration by parts and then bring it out, it turns out to be still 0 because that psi is vanishing at boundaries, but psi, like derivative of psi is not vanishing.
No, h psi is chi. Psi star h is also only chi or chi star by definition, right? So, this is Hermitian conjugate. H psi is chi. You agree with that? Which means H is some matrix, psi is this column. So, this will give me a column. This is your chi. Okay? Now, H star or H is Hermitian, this object is Hermitian conjugate of that, which means it is going to be chi star. In this case, it is not a problem because it is only real, chi star is same as chi.
But the moment we write a state vector or something like that,
so that is what the meaning I have given.
We end up with some eigenvalues. The moment we write it in terms of
no eigenvalues here. They are not pure eigenstates.
No, sir. Like let's say if you try to write psi in terms of Fourier series, you have some eigenmodes plus a constant, and that constant will never vanish.
No. In this case, completely you will get h psi star h is only 2n. Exactly you will have in this case. You can check it out. But I don't think you are right because this object, that is why I wanted to introduce this notation psi h. In fact, we are going to use it again, this thing. So, this object is chi and this object is chi star, chi this way. That is the way it is. Okay, that is all that happens in this case. I can work it out for you if you have some patience because it will take more time. I can work out from this also. I can sum that series also. Incidentally, I can sum that series because finally I know the number. I can find the sum of the series also. Okay? It is not very difficult. So, this is what you will get in this example. The reason why I am giving this example is only one reason. The reason is the following. So, the space of functions, square integrable functions is what I called as a Hilbert space, right. Let me call it as some big, any point in this space, in this thing is a vector in that Hilbert space, any point, okay, in that space. Now, you have some operator, let us say an operator like x hat. Okay. You have an operator x hat or p hat. Now, what is x hat? X hat operator acting on, let me take some function psi. I will have psi of x. I will have x times psi of x. This is the meaning of that operation, right. And I said psi is a square integrable function, which means psi star psi integrated will be 1 or finite number. That's what that function, square integrable function. Okay, psi of x is a square integrable function. If psi of x is a square integrable function, is it guaranteed x psi of x is square integrable function? Okay, that is simple question. If psi of x is some function, so the integral, this new function is x square psi star times x psi and then dx. This is the integral, right? X psi, x square psi star psi. That's what you should find out. Is it square integrable? That is a question. Okay? I will give you one example. One example is, for example, if psi, in order to say psi star psi integral dx from minus infinity to plus infinity, it should be less than 1 or less than infinity or finite number or 1. In order to make that as a finite number, the behavior of that function psi of x, okay, because there is a dx here. If psi star psi is not there, integral dx will come. Integral dx is infinity, right? So the value of psi cannot be a number at infinity. It should go like, because this goes like x, very large value. So the psi should go to infinity less than 1 by x power half. Less than that, because there is a x power half will give you 1 by x. Dx by x is log x, and log x also is infinity. Okay, from minus infinity to plus infinity. That's what will happen. So it should have something like, it should behave something like half plus some alpha here. If it goes like x power half plus alpha, psi star psi will be x to the 1 by x power 1 to alpha. That integral dx by x power something greater than 1. Okay, this integral is finite. This integral is finite. Say alpha. Anything, any alpha, not equal to 0. It is always finite, because at infinity it goes to 0. Okay, it goes to 0. So this, because there is a dx which tells you that. So if a function which is square integrable like psi of x, there is no guarantee x acting on that psi of x will give me a function which is square integrable. Okay. Now this is true for not only x, it's true even for p of x, p, it's true for Hamiltonian various operators which you have. So these operators which you have, they cannot act on all states in the Hilbert space. They cannot act on all states in the Hilbert space, because the resultant vector which you get is no longer square integrable. So you act on some vector, it will go outside some other vector, but that is not square integrable. So acting on this, these are all square integrable functions. But some operator here, it will go to chi, but that chi will be here. It goes outside that. It goes outside that. That's why we want to act on the square integrable functions, only a subset of square integrable functions in which this operator can act. So that subset is called the domain of that operator. It is called the domain of that operator. It is that operator on which the wave vector, if it acts, it will not go outside the Hilbert space. Okay, it will not go outside. So this is a problem whenever you have infinite dimensional vector spaces. So if you have infinite dimensional vector spaces, an operator cannot act on, such operators cannot act on all vectors in that Hilbert space. All vectors in that Hilbert space, because it will go outside. So it will have a subset of vectors in which you can act, and that subset is called domain of the operator. That's a very important point. Why is it very important is, we normally tell in colleges and courses, etc., you have an operator A, you find the Hermitian conjugate of that operator, right? I suppose this is what you are told. I am going to erase these parts. I am going to, you have an operator A, I am going to define what is called dagger, a dagger, Hermitian conjugate. If you are given a matrix, how do you do it? You take transpose and conjugate. This is what, I suppose you know this, right? You say A transpose and conjugate. This is what you say is a Hermitian conjugate of that matrix or operator in that space. Is that known to everyone? Everyone in the back? So then what you say, an operator is self-adjoint or Hermitian, okay, if A is equal to A dagger. If A is equal to A dagger, you say that this operator is self-adjoint or Hermitian. This is, I hope that statement is known, everyone? Yes or no? Please tell me. So, why is it we are interested in Hermitian or self-adjoint operator or thing matrix is the eigenvalues of this matrix, self-adjoint or Hermitian matrix, is always real. It cannot be complex. Okay, it cannot be complex. All operators which are self-adjoint or Hermitian, the eigenvalues are real. Now we want to associate our observable like x, p, etc. When it acts on some state, expectation values which you try to find out, we want to get only real values, because it is going to be only combination of eigenvalues. So all our measurements should lead. For example, when you look into the galvanometer or ammeter or anything, you are going to get a real number. You are not going to get the complex number there, right? So the eigenvalues must be real. So in order to have that, we say that all Dirac, when I said yesterday, he associated for every classical observable operator associate. X goes to x hat, p goes to p hat. That is the way he associated. They are called observables. When you say observable, the measurement of that operator will lead to a real value. That's why we want them to be Hermitian operators. That is one of the reasons. There are other important things. The eigenfunctions of these operators, these Hermitian operators, they are all orthogonal to each other. If you have two eigenvalues psi 1, psi 1 and psi 2, psi 1 star psi 2 integral will be 0. You don't have to do anything. It's almost like sine n pi x, sine m pi x. Let me make sine n pi x and psi m pi x. Integral from 0 to 1, if you work it out, you will find it to be 0. If you work it out, you will find that to be 0, right? Integral of that is 0. That's what you will have. So these are all various properties of such operators. Now these things work out correctly as you expected, whatever you have been taught, as long as you are in finite dimensional matrices, finite matrices. The moment you go to infinite dimensional things like this, it is not enough to say this is self-adjoint. We always say Hermitian is self-adjoint. Okay? But that is true only if the matrix is finite dimensional matrix. If it is infinite dimensional matrices where you have all these problems, then there is one more condition needed to say it is self-adjoint. And that one more condition is the domain of the operator A should be equal to domain of the operator A dagger. These two conditions should be satisfied in order that operator is self-adjoint. If you don't have that, that problem will be there. So that is one of the reason, which is also in this case, which affects all our problems. Okay? In this correction, I am going to give you one more exercise. That exercise is simply, I am going to give you a one-dimensional problem and ask you to find the energy eigenvalues. Okay? What is that problem? The problem is again R, which is minus infinity to plus infinity, and the potential, I have to give you the potential. I have to give you the potential, and this is a very peculiar potential which was cooked up by Dirac, and that potential is minus G delta function. Have you heard of delta functions? You have heard of delta functions? Those who have not heard of it, please raise your hand. Those who have not heard of it. You have not heard? Anyone? Others? Because I am going to give you a 1 minute introduction to delta function. It's 1 minute introduction to delta function. It's a actually mathematicians will not call it a function. Okay, but such a function is needed. So they will call it generalized functions. Okay? So we will use physics being like slightly loosely used. So we will call it as a function, delta function. This is what Dirac used, Dirac delta function. It's also the name. The function is, so in this interval from minus infinity to plus infinity, it is 0 everywhere else, everywhere. The function is 0. The function is 0. Okay? And at this point at x is equal to 0, it is actually infinity. The function is 0 everywhere from anything greater than 0 and anything less than 0, it is 0. And at x is equal to 0 is infinity. It's infinity. That is the kind of function. How do I visualize it? If you want, I have to draw one line here, to say that is the function. At that point it is infinity, everywhere it is 0. Okay? That's what delta function. But to understand it better in a physics language, what you can do is, you have the line from minus infinity to plus infinity, and you have a small width here A. At this point, you draw a rectangle which is 1 by A. The height is 1 by A. The height is 1 by A. The width is A. So what is the area of that rectangle? 1. You take the limit A tends to 0. What is the area of that rectangle in the limit A going to 0? It's again 1. So that is what is the delta function. It is actually take this rectangle, squeeze it such that the area remains always 1. Right? Area remains always 1. That is the kind of function. Okay? That is the kind of function. So the interesting thing is, I have this potential So it is minus, so the function is going to look like this. It's going to look like this, the value is g times that function. The interesting thing about that is, I am going to ask you to compute energy eigenstates of this. Energy eigenstates of this problem. Now, if it is simply that function is potential is not there, it is only free particle. It is only free particle. If this is not there, I can ask you to find the energy eigenfunctions of that operator. Now, what are those operators? What are the energy eigenfunctions for a free particle? Anyone knows? You want to find out h psi is equal to E psi, where h is p square by 2m, which is minus d square by dx square, apart from that h bar square by 2m. So you want to find out solution for this. Let me write h bar square by 2m, E times psi, or d square psi by dx square is minus 2me by h bar square psi. Okay, that is the equation you have to solve, and it is an equation which can be easily solved, and that equation is e to the power ikx, where k is that square root of 2me by h bar square, square root of that is what is it. Okay, so that is the value of that thing. Now, is it a good function, wave function? Is it or not? Yes or no? No. No. How many people said no and how many people said yes? Is it no? Who else? No. Then there are a lot of half hands. Okay, fine. It is not a good function because it is not square integrable. If you integrate e power ikx psi star psi, as I told you, e power ikx into e power minus ikx will give you 1. Integrate it from minus infinity to plus infinity, you will get this thing. So you cannot have that as a wave function in this thing from minus infinity to plus infinity. So what I will do is, I will put that in a box from say minus L to plus L. Then within that, that's a nice function. Within that, I think outside it is 0. So what you can do is, in general, a function like integral, okay, a function psi of x like integral dk e power ikx f of k, okay, that kind of function can be square integrable. Okay, that kind of function can be square integrable because I have put an fk. For large values of k, it can go to 0. So this kind of function is called a wave packet. So if that k is 0, you will have sine or cos function like this, sine or cos function up to infinity, e power I k is cos kx plus I sin kx, right, that is what you will have. So that is not a good function for us because integral is not 1, square integrable. But if you have a function, like this, if you have a function like this, it's nice function. Okay, that is what you will create by collection of several waves, and make it into a wave packet. It's not one wave, it's a collection of waves, and that is a packet, and that packet moves collectively together. That is what you can do, okay? That's what you can do, and that is what is the wave packet concept which is there always. That's what de Broglie wave, which he used, de Broglie wave packet. He had a group velocity, phase velocity, etc., comes from there. Now, given this, my problem is for this exercise, for this potential, which is delta function minus g delta of x, okay, find out the energy eigenvalues if it is there. But you should remember, it is everywhere is zero potential except at that point. There are two ways of computing it. You can have this kind of a box which I have rectangle with potential height is 1 by a, the width is a. Find out what is the, is there a bound state or energy eigenstate for that, and take the limit a tends to 0. That's one way of finding. It is more complicated way of finding, because if you have that kind of a problem, a box, okay, you have to apply the potential, solve the problem inside the box, outside the box, and then match the boundary conditions, But it so turns out that this problem can be solved without that kind of complication. And it is related to the kind of thing which I was always telling you about the nature of the wave functions, etc. And this is the answer. So I will leave it at the moment as an exercise. Okay, is that okay? Is that enough? I am going to start, already taken too much. So I am going to start with other than particle in a box. I am going to start with a very simple introduction to harmonic oscillator. So harmonic oscillator, okay, simple harmonic motion, simple harmonic oscillator, and I am going to solve the problem, okay. I am not going to use the regular way in which the textbooks solve, but I will solve it in some little more matrix mechanics, which probably is good. So the Hamiltonian is one dimension, p hat square by 2m plus v of x is half kx square, right. This is what is a harmonic oscillator. The spring constant is k, the mass of the particle is m, and if you pull that thing by the spring, it is connected to a spring, that mass will oscillate, it will oscillate. Classically that is what it will do. So I want to do the quantum mechanical problem of this thing, which means I should find out solutions for this equation. Where this is actually h bar square by 2m d square psi by dx square plus half kx square psi is equal to E psi. This is the differential equation which you should solve for among square integrable functions, The function should be square integrable, which means whatever solution you should have, it should be, if you integrate psi star psi, it should be 1 or some finite number which you can normalize it always. That is what is required. So not all functions satisfy this equation, and the solutions, do you know the solutions? Yeah, Hermite polynomials. It's more than Hermite polynomial, but with the Gaussian, yes. So I will give you the solution, but I am going to not solve the differential equation, since in gory detail I will give you the solution. So psi n of x, where n can be 1, 2, 0, 1, 2, 3 up to infinity. Any number, integer, 0, 1, 2, 3 up to infinity. I'll write down the solution, okay, in this basis, which is equal to 1 divided by 2 to the power n factorial square root. This number which I have put is a normalization constant, because the rest of the functions which I have given you, if you integrate it, you will get some finite number, you divide by the square root of that. That is what is the thing. And then you will have m omega divided by pi h bar to the power 1/4. It looks messy, but I will give you anyhow. And then e to the power minus m omega x square divided by 2h. There may be some typos here, 1 omega square or something may be there, I do not have to check. And then Hermite polynomials, which a friend mentioned, it will be some number by, m omega by h bar times x. Okay, that is the function. Now this object Hn, it's written in gory detailed solutions. It looks little complicated. The Hns, Hn of 0, H0 of x is 1. H0 of x is 1. H0 of x is 1. H1 of x is 2x. And H2 of x is 2 minus 2 plus 4x square. H3 of x is, I suppose it is 2x or 12x, minus 12x plus 8x cube. I have given some first 4 values, 0, 1, 2, 3, but the number will go on up to infinity. N can go from 0 to infinity. That is the way of the harmonic oscillator. So this is what is this thing. And if you are interested in doing only functions and calculations, etc., you can sit and calculate this quantity and I will give you the answer. Don't even try to do that, it's a messy. There are other ways, simpler ways of doing, and you can find out the expectation value of x hat square between 0 and 0. This is what is meant by that is psi naught star x square psi naught integral dx. This is what is meant by that. That is what I have written down. If you do that, you will get the answer as h bar by 2m omega. And if you do that for p square, if you do that for psi naught square star minus d square by dx square psi naught multiplied by h bar square by 2m whole square and then dx. If you do for this, you will get the answer as m h bar by 2m omega. Sorry, 2, that is all. This is what you will get. Okay. Now, doing such integrals are not very difficult, and probably in the examinations they threaten you with evaluating many of these things. Okay. It is essentially working out Gaussian integrals. The integrals are of this form. If you have that integral from 0 to infinity or minus infinity to plus infinity, if I ask you to work out this integral from minus infinity to plus infinity, what is the answer for that? Root pi. Okay. Okay, he says it's root pi, let's believe probably it's correct. How do you get it? How will you get it? How will you find it? Either you look into the tables and then get the answer, or if I ask you to work out from first principles, like a regular integral, how will you do it? Anyone? Yes? Polar coordinates. That's correct. So what is the thing is, you write down I square, this is I. Then you will have minus infinity to plus infinity e power minus x square, e power minus y square, dx dy. You go to dx dy, you go to r dr d theta in polar coordinates. This will turn out to be e power minus r square integral. So e power minus r square r dr is easy to work out, because you can say r square is t, and then it is only integrating e power minus t from 0 to infinity. That's, and d theta will give you the 2 pi factor. Since it is square, it will turn out to be square root answer. So this is the way in which all other things here with Hn is very easy to work out. Okay? Supposing I ask you to work out this quantity. Well, if I ask you to work out this quantity, e power minus x square x dx, what is the answer? No, e power minus x square x dx, from minus infinity to plus infinity. Anyone? He says it is 0. Anyone who is not agreeing or disagree of a different value? E power minus x square dx, x dx. Huh? What? Yes, x is an odd function and e power minus x square is an even. So if you integrate it from minus infinity to plus infinity, you will get it to be 0. As simple as. So if you have x square, you will have non-zero value. X square, if you have, you will have non-zero value. Right? That's what you will have. How will you work out that? Yeah. So that is the way which has to be done. So simple way is, you write this integral e power minus alpha x square, no x square here. Find this as a function of alpha. Find this as a function of alpha. Right? Root by alpha. That's what you will have. Right? It's the same integral. I'm not doing anything more. I have only scaled x by alpha x. That's what I have done. Okay? When you do that, you will get root pi by alpha. Now, if you want to get e power alpha x square, what is it you want? This thing, if you differentiate this with respect to alpha, you will have x square here. Right? So, if you have the function I alpha, you can differentiate it with respect to alpha and put alpha is equal to 1. That's all. As simple as that. There are all simple tricks in integrations which you can do and get the thing, and any Hns which you have, I have already given, the integral of those things with any powers etc. can be worked. Any power of x power n integral can be worked out. Okay. This is only what is the functional things people will do, and I am not going to do that. I have given you this. And this is something probably many of you will know, people who have done the thing, but I am going to tell you a little more about it. What is the little more? Okay. I am going to define an operator instead of x hat and p hat. I am going to define an operator A. This is not a Hermitian operator. X hat is a Hermitian operator. P hat is a Hermitian operator. But this is not Hermitian operator. And our operator I define, to make life simple, I will do some tricks later. m omega by 2 h bar square root x hat plus I by m omega. I'll tell you what is that omega is. This is the one. That omega is, omega square is k by m. This is the frequency of the oscillator. That's the frequency of the oscillator. The oscillator oscillates with that frequency. Okay? Now, in order to make life simple, I yesterday introduced, my friend was objecting, and I will, my colleague was objecting, you should not introduce such things at the BSc or MSc levels, and I will still do it. I will call h bar as 1. Okay? H bar is 1. I am going to do one more. I am going to make k is 1, m is also 1. Right? Mass of the particle is 1 in my hand, and the spring constant is also 1. It's also in my hand, so the problem becomes simple. In that case, my Hamiltonian is half p hat square plus x square. As simple as that. In that case, right? That's all the Hamiltonian. Where minus term? No, p is minus I h bar, but p itself, p square will have, the differential operator will have, but this will not have. Okay? So p square is p is Hermitian operator, as I told you. So if p is Hermitian operator, it has only real eigenvalues. It has only real eigenvalues. If you diagonalize it, it will have along the diagonal some real numbers. It may have minus 2, minus 3, plus 2, plus 3, all those things will be there. But p square is only square of those numbers, so it has to be always positive. Sometimes we call it as a positive definite operator, positive operator. What about x square? Again, it is both positive and negative values it can have. So that is also, square is positive, it's only positive. So p square plus x or Hamiltonian is a positive operator, positive definite operator. It at most it has 0 eigenvalue and anything above that, but it cannot have less than that, right? It goes from 0 to infinity, but not from 0 to minus infinity. That is the kind of operator which you have here. Now, in this notation, A is equal to, if k is equal to 1 and m is equal to 1, omega will become 1. So this object which you have is 1 by root 2 x plus I times p. What I have done is p square plus x square, which you have, or you know this, x square plus y square. If I define x plus iy is z, x plus iy into x minus iy will be x square plus y square. That's what I am going to do. So there is another operator which is a dagger. A dagger 1 by root 2 x hat minus ip. There are two operators which I have introduced, a and a dagger, which is essentially p square plus x square. That's what you go from Cartesian to polar coordinates, right? R is that x square plus y square, right? That's what is there. That's what I am doing here. Now, we know that x operator, p hat operator, commutator is I. I have taken h bar as 1. That's what your Heisenberg commutation relations tell you. So I can find out what is the a dagger commutator. You can find out, okay, and take it as an exercise, and many of you know the answer. Answer is 1. It is 1. It is 1. It's actually 1, and that Hamiltonian which you have here is a dagger a plus half, half times this one. Am I right? No, A dagger A plus half. This is what the operator will turn out to be. Okay, it will turn out to be this operator, A dagger times A times plus half. As simple as that. So instead of operators x hat, p hat and Hamiltonian, I have made into A dagger and H, which is A dagger A. So this is what the operator is, and I want to find out H psi is equal to E psi. Solutions for this equation. Yesterday somebody was asking me, you said x hat is a matrix, p hat is a matrix. I am going to give that matrix now. I will give you that matrix now. Now first let us find out eigenvalues of this operator. Now the eigenvalues of this operator, essentially I will call n as an operator which is A dagger A. We will call that operator as number operator. We will call it as a number operator. We will see why it is number operator. So what you will find is, if you have some state, I will call a vector n, which is essentially something like infinite dimensional somewhere, some maybe 0, 0, 0, 0 and 1 here, 0, 0, 0. That kind of vector, okay, infinite dimensional vector. Because I told you all our vector space is infinite dimensional, I will have various vectors, up to infinite number of components will be there, and the nth component is 1, the rest of them are 0. So let me take that kind of a vector. Or a linear combination of that. The interesting thing you will find is, if this n is an eigenstate of A dagger A, if it is an eigenstate of A dagger A, with eigenvalue, let me call it as some n itself, with this number n, you can call it a function of n if you want. You can call it a function of n, you do not need the thing. Then A dagger acting on this n will be a new state n prime. It will be a new state n prime. A dagger is going to give you a new state. The n prime is also an eigenstate of A dagger A. N prime is also an eigenstate of A dagger A. The question is, what is its eigenvalue? The eigenvalue of that is 1 above n. So if I have said n here, it is f of n plus 1. F of n plus 1. Or if it is n, it will become simply n plus 1. So A dagger will rise, it will go one ladder above, in the ladder one step above. You act by A dagger square, you will go one more steps, 2 steps above. A dagger cube will give you 3 steps above. What about A? A will do the opposite. So A acting on n will give you n prime, n double prime, let me call it n double prime. This A dagger A acting on n double prime is n minus 1. N double prime. So what does it do? A lowers it 1 unit, etc. You might have started with 2.5, it will go to 1.5 and then 0.5, etc. But after acting by 0.5, okay, it will go to minus 0.5. A dagger A will be minus 0.5. But I have already told you that A dagger A or Hamiltonian is positive always. It cannot have any negative eigenvalue. So which means it should go to only 0 eigenvalue. The lowest eigenvalue of A dagger A has to be 0. Anything below that, nothing will happen. Okay? So that is a kind of thing which you have here for this problem. So you will have A dagger A acting on n, give you n times n, where n is 0 to 1, 2, 3 up to infinity. And A acting on that state gives you n minus 1 state, n minus 2 state, and A acting on 0 gives you 0 because of this thing. So A acting on 0, gives you 0. It kills it. People will call it as a vacuum state or ground state, the lowest state. You cannot go below that. You cannot go below that. Okay, that is the ground state, A acting on 0. So what you have actor acting by A dagger, 0 will become 1, 1 will become 2, 2 will become 3, etc. on that ladder. If you start somewhere else in some 10, by acting by A, you will get 9, 8, 7, 6, 3, oh I missed, continue correctly, go up to 0. You can't go below that. So this operator, A dagger, is called rising operator. It rises. And A is a lowering operator. In the ladder operator, it's called ladder operators. In the ladder, one is rising and another is lowering. If you do further, you will find some people call it as a creation operator. If there is one particle, one quanta, it will become 2 quanta, 3 quanta, 4 quanta. And A will be reducing it. If there are 4 quanta, it will become 3 quanta and 2 quanta, etc. One is called creation operator, another is called annihilation operator. And A dagger A gives you the same operator. Okay? So if you take a book on quantum mechanics by the Japanese physicist called Sakurai, in his introduction, he calls this A operator, A dagger operator, and N operator, as A is, in Hindu mythology, you have Shiva who annihilates, and A dagger creates, Brahma, and Vishnu provides whatever prosperity we want. He called it as the Trimurti. The A dagger and N are the Trimurti. In that book, I was surprised that this guy from Japan is talking about this, but it was interesting. So this is the way in which these three operators act on. It's called Sakurai quantum mechanics book. So this is the nature of these operators. Okay. So somebody wanted, what is my X? Is it a matrix? And I'm going to give you the matrix because my states are, so I can erase all these things. The lowest state is the ground state, 0. I call it 0. And I am going to write the vector. This is my vector for that, 1, 0, 0, 0 up to infinity. That is my ground state. You cannot go below that. What is the next state you can go? 1 is 0, 1, 0, 0, 0, 0. That is the next state. And 2, I will erase here and write it. I will erase here, write it here. The third position, fourth position is 1. That is a collection of vectors. Any vector is a linear combination of them. Any arbitrary vector will be, write A1, A2, A3 up to infinity. That's all. Which means if I write any state sign is AN, N, it simply means A1, A2 up to A, somewhere AN and somewhere A infinity also. Okay, that's all that is there. That's that vector. Now, in that space, I can write down my A's and A daggers. Let me write down the A's and A daggers. Let me try to run a little fast. Am I going very slowly or fast? You have to tell me. You have to tell me, am I going very slowly, or for him it might be slowly, might be knowing already. But for some people also. But I am trying to average out. So the operator A dagger, it is a matrix. I told you it is a matrix. It transforms one vector to another vector. What does it do? A vector with nth number, n position is 1, it transforms to n plus 1. That is what is the thing. And I will write down A dagger for you. That matrix is 1. It is actually 1, root 2, root 3, root 4, etc. Okay? That is why is it, where is that root 2, root 3, all those things come? In order to see that, you have to find out A dagger acting on n. If you actually work it out, it will turn out to be root of n plus 1 times n plus 1. Why is it so? N may be normalized. Your state n may be normalized. N will be, I will write it this way, this notation 1. But A dagger n, and then this is what is this state is supposed to be, and then complex conjugate of that is this. If I do this, this is some n plus 1. Okay, you have to take the square root of that. So that is what will happen. So this is the result. So which means the connection between nth state and n plus 1th state, there is a factor of root n plus 1. Similarly for, and here I will write, these are not needed. A, the operator A is same matrix, just take the transpose. A dagger, if you take the conjugate, you take the conjugate and star. But here it is enough if you take transpose and star, but it is enough if you take the transpose because it is a real matrix. It is 1 here, 0, 0, 0 here, root 2, 0. Diagonal terms are 0. The diagonal terms are 0. Off diagonal terms in the first off diagonal, just above the diagonal, they are all 1, 0, 1, 2, 3, 4 up to square root of that. Similarly. Now we have this definition which I gave you, A and A dagger. From that I can write down x hat operator. X hat operator is an A plus A dagger, apart from 1 by root 2 or so. Okay. So it's only, I have given you two matrices, A and A dagger. Just add the two matrices. That is your X. So yesterday somebody was asking me, is X is a matrix? Answer is yes, X is a matrix. The operator X is a matrix. Similarly, the momentum is a matrix operator. In acting on the space of states which are labeled by 1, 0, 0, 0, 1, 0, 0, 0, 0, 2, all those things, collection of all such states, you take it in that space, your X hat operator is simply this. Simply add. It will be Hermitian automatically. It will be nice operator which you want to have. Okay, this is what is the operator X hat is. Okay. So this is the whole thing about harmonic oscillator problem, which is very simple, and I gave you to start with eigenstates in terms of e power minus x square, etc., etc. How do I get them from here? Okay. I told you in matrix notation, Heisenberg notation, you may want it in the terms of Schrodinger representation. To do that, it is very simple. It's very simple. It's very simple. A acting on 0, the ground state is 0. A acting on 0 is 0. But A I have defined for you earlier. It's some 1 by root 2 x plus IP acting on 0 state, the lowest state is 0. But now you know what is P hat. It is minus IH bar. So this is here plus d by dx. IH bar, H bar I have taken to be 1, minus I and plus I will make it as plus 1, and this is the thing. And this is, I will call it as psi 0, the ground state. You don't need this root to here. This is a simple differential equation. It's a very simple differential equation. It will be x plus d psi by dx. X psi is, or d psi by dx is equal to minus x psi. That's all that equation. You solve it, answer is e power minus x square by 2. It's a Gaussian. It's called Gaussian. E power minus x square by 2 is the solution. The solution is, you can solve this and you will get psi naught is equal to e power minus x square by 2, apart from normalization factors. Okay. Now you got what I gave you in the exercise thing. I gave you general solution psi n in terms of Hermite polynomial, etc., etc. How do I get the next one? You act on psi naught by A dagger. But A dagger is what? I have already given you the thing, differential operator. You act on that by x plus x minus IP. You act on that, you will get a new function. That's your next high one level above, 2 levels above, etc. All of them can be easily worked out. So this is one way of solving is what was Schrodinger equation, solving is a differential equation. And another way of solving the same set, same thing, is by Heisenberg mechanics. Okay, one is Heisenberg picture, another is Schrodinger picture. That's all, as simple as that. Okay, there are some interesting things that can happen now, and that's what I wanted to tell in the next 5 minutes, and then I will slowly move to the angular momentum. I want to start with angular momentum today and then get some idea. Okay, I have, the states are, now I am going to have a new Hamiltonian in 2 dimensions. What is the new thing? It is half px square plus py square plus x square plus y square. I will have the frequency for both the oscillators same, one and the same, which means 2 oscillators. Instead of 1 oscillator, it is 2 oscillators. As simple as that. Now can anyone tell me what is the eigenstates? What are the eigenstates for this problem? It is simply adding one more, right? Whatever you did with x will happen for y. So the x has set of eigenvalues given by n, right? Eigenvalues are given by n plus half. Now y will have again another n. Instead of calling it as n, you call it as m. So the general state is going to be labeled by 2 numbers, n comma m. One for x, one for y. One for x, one for y. Okay? So this is going to be n, comma m, and the E will be n plus m plus, so you had n plus half and m plus half. So it will be n plus m plus 1. It should be multiplied by h bar omega. It should be multiplied by h bar omega. For my unit, h bar is 1, omega is 1 for my unit. Otherwise, you should put that also. So what are the eigenvalues now? N plus m plus 1. A state is n comma m, and the eigenvalues are n plus m plus 1. Is that clear to everyone? Because I am going to ask further questions. If you say yes, you should answer also for the question. Better say no. Is that okay? You are ready? So what is the lowest state, ground state? 1. What is the state, how will you label it? N is equal to 0, m is equal to 0. So let us write down that. So you have the state n is equal to 0, comma 0, and the value is 1. E energy is 1 unit, h bar omega, 1 unit of h bar omega. What is the next state? Higher 0, higher than 0. Yes. So you can have n is equal to 1, n is equal to 1 or m is equal to 1, and the value is 2. Value is 2. Correct? Agreed or disagreed? Yes or no? Yes. Next state is 1, 0, 0, 1. There are 2 states now. There are 2 states now, and both have value 2. We will call it as degenerate states. Something very nicely, degenerate states. Okay? From this exercise, I am going to do several things, which is going to bother about next, yes, tomorrow and day after also, tomorrow as well as angular momentum. So let me go further down. What is this next one? 0, 2, 2, 0, and then 1, 1. Let me call it as 1, 1 first, and then 2, 0. Okay? You can have n is equal to 2, m is equal to 0. You can have n is equal to 1, m is equal to 0, 1, and n is equal to 0, m is equal to 2. The total is how much? 3. Okay? So energy eigenvalue 3 has 3 states. Energy eigenvalue 3 has 3 states labeled by 0, 2, 1, 1 and 2, 0. Energy eigenvalue 4 will have how many states? How many states? 3, 0, 2, 1, 1, 2 and then 0, 3. 4 states. Energy eigenvalue 5 will have 5 states, etc. Right? This is what you have. So the number of states, degeneracy of the thing goes by 1 unit above. It has 1 state, 2 states, 3 states, 4 states, 5 states, etc. for this problem. So the degeneracy here is related to certain things inside that Hamiltonian itself, because there is nothing, there is an x, there is a y. You can put 2 here, 0 here, or 0 here and 2 here, or 1 here, 1 here, right? That's what, it's like 2 boxes. In the 2 boxes, you want to keep number 3 chocolates. So you put 2 chocolates in 1 chocolate here, put 3 chocolates here, 0 chocolate here, or something like that. That's all. In fact, probably in statistical mechanics classes, that's what he did, right? Probably, I don't know, has he started something like this in statistical mechanics? No, not yet. Okay, fine, he will probably do it, because what is it you are going to have? you are going to start with the number of states in that box which you have. That's what you are going to have. So this is a very interesting thing to start with. Okay. So this is the way the whole thing is going. Okay. I don't know whether I'm going to start now, and what I'm going to start is about angular momentum. Have you heard of angular momentum? R cross P. R cross P. Now the angular momentum value, probably you might have heard, it is specified by a number j, and j can be 0, 1, 2, 3, 4, any number. The number of states in that is 2j plus 1. Are all the people aware of this? If you have done hydrogen atom, this is what you will have, 2L plus 1. Let me not call it J, let me call it as L. You will have angular momentum is specified by L, and ground state will have 0, no degeneracy. The first state, L is equal to 1, will have 3 states, 2L plus 1. The next one will have 5 states, 2 into 2, 2L plus 1. That's what we'll have. Now that is what is happening here. Ignore these things. Ignore these things. The next one, all the even things you ignore. All the odd things you have, 0, 3, 5. It looks like some angular momentum coming up, right? Angular momentum coming up. Now you might have heard of spin angular momentum. Electron has spin value which is half, and it can be spin up or spin down, 2 states. So in addition to angular momentum R cross P, if you have a spin also for electron, hydrogen atom, the states will be, it can be half, spin half, which is again those omitted things which I have here come out in that, right? The 2 state is only spin up and spin down. And the next one, 0, 2, 2, 1, 1, 2, 0 is like spin value, angular momentum value is 1, which has 1, 0, minus 1. It's what is that, is it? Okay? In fact, if I tell you, you take this n, you take this m, you take this n minus m, half of n minus m, okay? So what is half of n minus m for this? It is 0, right? For this, there are 2 states here, n minus m is what? N minus m is minus 1, right? Half of that is minus half. And the next one is n minus m is 1, n minus m is 1, half of that is half. It's like plus half and minus half, spin up and spin down. Now let's go to the next one. What about 0, 2? N minus m is minus 2. Half of that is minus 1. So it's minus 1 state. It is minus 1 state, 0 state, and plus 1 state. You go to the next one, it will simply match. So the angular momentum things automatically come here in all these things, okay? And that's going to be my next theme. Where is that angular momentum built here? Angular momentum is related to rotations, right? Angular momentum is related to R cross B is related to rotations. I can understand rotations between x and y, but it's not a 3-dimensional rotation. It's only 2-dimensional rotation. Whereas we find what you have in 3-dimensional rotation is appearing here. Where is the 3-dimensional rotation coming from? That is the symmetry which is there already, and I leave it to you, think about it, where is it coming from, and if possible today afternoon I will be here for the tutorial. If I am around, I will come, I will explain that part. Now I am going to the angular momentum. Remember all these things because it will come up again. Okay. Okay, let's go to the angular momentum. Angular momentum operators, or you have heard in classical mechanics, is given by R cross P. You are aware of it, right? This is your angular momentum operator L as a vector. So let us write down Lz is going to be xpy minus ypx, and Lx is going to be ypz minus zpy, and Ly is going to be zpx minus xpz. These are the operators. These are the dynamical variables in classical mechanics. You know this, right? R cross P. Now what I want is make them operators. So I am going to put them as operators. It's only putting the hat. All of them you have here. So take it as an exercise, which you have done earlier. Find out what is Lx, Ly commutator. Lx, Ly commutator. Now I have given that as operators, right? You know the relation x px is I, y py is also I, z pz is also I. The rest of them are 0. The rest of the combinations are 0, right? So you can sit and compute, at least once you should do that. You can find out for one, Lx, Ly. If you find for Lx, Ly, you can easily find for Ly, Lz, you can find for Lz, Lx, Lz, all those three things, because it's only change x to y to z. It's a cycle, okay? So at least try to do one, Lx, Ly commutator. Anyone knows what will be the answer? Because you have studied in, yes? Lz. So now my h bar is 1 in my unit. That's why I have put I here. Otherwise I should have put h bar. So this will be I times Lz. Okay. So that is what is the angular momentum. So now I should find out matrices corresponding to that. Because I have already found out matrices for corresponding to x hat, p hat, all those things. Now I should do for these things also, because now they are all operators. Okay? So I will write down in some nice notation. I will write down in some nice notation. So you have three operators Lx, Ly, Lz. And they are all operators. None of them commute. None of them commute. Lx, Ly is not 0, Ly, Lz is not 0, all those things. So you can't make all of them diagonal. If you make them diagonal, they will all commute, right? You can't make all of them diagonal matrix. At least only one matrix you can diagonalize. You can make it as diagonal. One of them you can make it diagonal. There is no problem with that. There is no problem with that. So let me make Lz diagonal. Lz is a diagonal matrix. It will have some number of states. Okay? So it will have some, let me call it as m. It will have m eigenvalue. It will have eigenvalues which are m. I don't know what is the number value m, but that's what it will have. Lz is diagonal for me. Okay? To start with. It will have positive, negative, etc., etc. Now there is one more. That's the interesting part. I compute what is called L square. Lx square plus Ly square plus Lz square. I call it L square and then I find out the commutation relation of L square with Lx. Okay, L square with Lx. What will it be? Anyone? Anyone? Why are you hesitating to tell? Well, that doesn't matter if it is wrong. 0, right. It will be 0. What is it you have to verify? You have to verify at least one matrix, Lx, enough. And it has to be 0 because Lx is doing a rotation. But it's like x square plus y square plus z square will not change whatever rotation you do, right? X going to x cos theta plus y sin theta, all the rotations you have learnt already. Whatever rotation you do, x square plus y square plus z square is invariant, doesn't change. What Indumati might have told us, x square plus y square plus z square minus c square t square. Something which is invariant, it will not change, right? So here also it will not change, so this is going to be 0. Similarly for Ly, Lz, right? Similarly for Ly, Lz. So this operator called L square commutes or does not have anything. So L square with Lz is also 0, correct? So if Lz is diagonal, I can also make L square diagonal because both are commuting. Commuting matrices, if they commute, you can diagonalize both of them simultaneously. That's probably something which I should have mentioned, that is there. So it should have some value, and for all practical purposes, we will call that number L square the state, and I will put that eigenvalue of that as j or L. I will call it as L into L plus 1. Don't ask me why this funny L into L plus 1, that's what comes out. Naturally, it is there in your hydrogen atom. L into L plus 1 is coming out, all because of this guy Legendre. He gave the polynomial, he didn't get simply L square, he got L into L plus 1, okay, and that's what comes out. Okay, so now you have a basis. The states are labeled, and I am going to stop here with this thing. L square acting on Lm gives you L into L plus 1 times Lm. Lz acting on L comma m gives me m into Lm. This is the basis because you have diagonalized both of them. What are the things you are left out now? You have Lx and Ly, right? Lx and Ly. And the interesting thing which you did with the harmonic oscillator, I will define L plus as 1 by root 2 Lx plus ILy and L minus as 1 by root 2 Lx minus ILy. I will define L plus and L minus. Why is it I am defining this? Because my knowledge about As and A daggers gives me something like that will help. And the interesting thing that helps is by using the same algebra which I have, which I call it algebra, angular momentum things, I will probably help you in the afternoon. The result is if you start with m, L plus acting on m will go to a new state that is also eigenstate of Lz, just like what you had here. N you started with, A dagger acting on that goes to n plus 1, but that n plus 1 is also eigenstate of A dagger A, right, Hamiltonian. Like that, if you start with an m state here, if you start with Lm and L plus acting on that will give a new state, let me call it as L m prime, but the eigenvalue of this state, that Lz acting on L comma m prime will be m prime m plus 1. One step above, it is a ladder operator, it just takes you one step above. Okay. L plus square will take you 2 steps above, L plus 3 L plus cube will take you to this. So L minus will lower it one by one. Okay. The most interesting thing is, unlike the case of A dagger A, etc., where it went up to infinity, here it cannot do that. It has to stop at some lowest value and it has to stop at some maximum value. It cannot go above that. You can't go above and below. I will explain why it is so. So it will actually go from minus L to plus L. The m value can be only from minus L to plus L. So if L is 1, it can go from minus 1, 0, 1. If L is equal to 2, you will have minus 2, minus 1, 0, 1, 2. That's your state, number of states is 5. Okay? If you start with 3, minus 3, minus 2, minus 1, 0, 1, 2, I can't go above 3. So there are 7 states, 2 into 3 plus 1. So that is what is going 2L plus 1. All the matrices which you have now, L plus, L plus, L minus and LZ, or Lx, Ly, Lz. These 3 states, these 3 operators are finite dimensional matrices. Unlike the previous case where you have infinite dimensional matrices, here you have only finite. 3 by 3 matrix, 2 by 2 matrix, 5 by 5 matrix, etc. That makes quantum mechanics even easier because you don't have to deal with infinite dimensional matrices. You don't have to deal with infinite matrices. It is enough if you deal with finite number of them. But that finite number can be very large number because L can be million. Then 2 into million plus 1 states will be there. Okay? So that is what is the idea. So this is what is our angular momentum minimal introduction, and then I will tell you more about some of these things if possible in tutorial and tomorrow also. And then later, if I do it in tutorial, I will, if possible, otherwise tomorrow. Then I will take up time independent perturbation theory, which is also related to this. For example, I gave you the degeneracy of level 1, level 2, etc. So I add x square plus y square in my potential, I add some x square y square potential, another potential, or x thing, or if I make it as x square instead of y square, I put 4 times y square. So the degeneracy will be lifted, okay? It will not be degenerate again. So that is a kind of a thing which will be of interest.